So I want to talk about an issue that's also related to savannas, which is the area that John Hargrove was just talking about a while ago. Savannas are much bigger than anybody seems to realize who isn't working in the savanna area. Okay, before I get there, let's talk about what I mean. So the natural vegetation, the rangeland, I'm going to talk about animals that are being kept for economic purposes, herded by people. Rangeland means the vegetation that plants they eat. It's just a natural vegetation. There's no attempt to plow or manipulate the vegetation, or not much attempt. There always is some attempt, fire and whatnot. A savanna is a seasonally dry area. So you have a dry season and a wet season. Fire is a very important part of keeping a savanna a mixture of grass. Okay. So fire is a very important part of keeping a savanna a mixture of trees and grass, and it is the most extensive. When I say largest, I mean the most extensive. It covers the largest area of any one vegetation type on the planet. The savannas are larger than the deserts, they're larger than the tropical forests, they're larger than the taiga, they're larger than the tundra, and all the other areas are small by comparison to those. The mega herbivores, here we see cattle, but there of course are very, very many other types of large animals, and many of them are actually specialized eating grass. The curious thing is that there is no climax, no clear climax vegetation for savanna. The two most closely related vegetation types are where you have no trees, you only have grass, or where you only have trees but you have no grass. So you have a forest or a grassland. A savanna has neither of those, but a savanna can be almost closed with trees. So you can have quite a dense vegetation of trees, but it's still a savanna. There's still quite a lot of grass. Or, as in this case, it's largely grass. There's only a few trees, and everywhere in between. Also, the trees can be quite regularly dispersed, or the trees can be very clumped. So the pattern, there's no really clear pattern, and part of that is the role of the animals, the role of fire, and also the role of rainfall. Now, in this context, people are trying to do rangeland management. So, of course, there's lots of traditional ways of rangeland management. It's a very, very old way for people to live, is to have animals that they're under their control, that they're herding. But it's only in the 20th century that the formal scientific efforts were made to advise what people do and to try and do the stocking on some kind of scientific basis. And the idea developed that there is, I don't want to do that, there is such a thing as an optimal stocking rate. So you keep X number of large stock units on Y number of hectares. And that is advice that's given to all the farmers in the area, and anybody who wants to do things differently is said to be unscientific. And the government is trying to impose this. And in South Africa, there was a very interesting natural experiment because of the apartheid regime. The good scientific advice was given to the commercial farmers, which were all the white farmers. And on those farms, you had a very low stocking rate of cattle and a lot of vegetation. And then the traditional farmers, the black ones, on their land, you had very high stocking rate of animals and very low vegetation. The conventional belief was that the commercial farmers were more productive. They certainly earned more money. But in fact, as far as at least in one situation that I know of, experiments were done, and the total yield of productive meat and milk and everything under the traditional management, where the vegetation was so low, was actually higher per hectare. So it's not an obvious thing, this idea that there is such a thing as an optimal stocking rate, and a lot of the dispute is actually about that. So one of the methods that people have suggested is a good way is to keep the animals in a small area but move them from time to time, so they eat a lot of the vegetation. Vegetation goes low in that area, you take the animals away, the vegetation recovers. After a while you bring the animals back. By that time the vegetation is recovered, there's a lot of food, and in this way it is said you can produce more with your animals than if you just let them run around and eat what they want to all over the place. And in fact, there's a lot of people who believe very strongly in rotational stocking. There's actually a strong research tradition that says it doesn't help. You actually do not produce more if you do rotational grazing. So associated with that is what one might call adaptive stocking. So rotational grazing is reasonably strict. You put the animals down for 4 weeks and you move them on for 4 weeks and you move them on for 4 weeks and you move them round and round, or for 3 months or whatever your particular pattern of rotation is. Adaptive stocking is where you actually adapt your size and concentration of your herd. So you have ways in which you can concentrate the herd or let it spread out. You can bring animals from other areas into this area. You can sell off animals. You can kill off animals. And there are very many traditional styles which attempt this kind of adaptation. There's also this thing called holistic management, which is associated with an ex-ecologist called Alan Savory. It's very controversial. And by controversial, I don't mean all the other things. I just mean scientifically controversial. There's been extremely strong scientific opposition to this idea of how one manages rangelands. But there has actually been some mild scientific support as well. So the scientific support is quite tentative. The scientific opposition is vociferous. But that makes it an interesting situation, I think, and it makes it a situation that I'm interested in trying to understand with modeling. So this is the kind of context in which I'm trying to suggest the modeling. And this is just a couple of words. I've mentioned the complexity. There are numerous objectives. You want to make money, you want to maintain the herd so that it's sustainable. You want to maintain the grass so that it's sustainable. There are lots of constraints. Some of the constraints are purely economic. It's not easy to sell off tiny amounts of cattle all the time. Or you make a contract which says you have to deliver a certain amount every month or every week. So these are actually difficult things to try and achieve. And that's just in terms of traditional optimization of planning and economics, but there are also tremendous variations in the environment which makes all of those things much more difficult. The opportunities and emergencies come and go, and that's why you have so many different styles, even the so-called industrial science styles which are associated with economic attempts. Well capitalized, you sell into the market, you get money, you buy lots of equipment, you spend fuel, you've got workers that you pay, and maybe you've got a president of the US that lives next to you. There are lots of different ways in which that's done. There are also lots and lots of different traditional methods which have developed over many generations, and many of them are still around even in the modern era. So in this context, we talk about a grazing management unit, which is just a set of paddocks and a herd. A paddock is not necessarily something that's physically fenced. It can be fenced in virtual ways. But a paddock is an area in which you confine a herd and which they then utilize for food, and you can move them from paddock to paddock. There is also machinery and people associated with the grazing management unit and a set of policies and all kinds of things like that. I want to focus on the concentration factor K and the stocking rate, tilde H. So this is not something that I've seen defined in the literature, but I think it's a very convenient item. So you can define it instantaneously as the area of the paddock, or maybe more than one paddock, occupied by the grazers at that time. And you divide that by the total area of the grazing management unit. So that's just the proportion of the total. Sorry, I actually want to use it the other way around. I see now I've used the reciprocal. I'm talking about K as bigger than 1, so it's actually the total area of the GMU divided by the area being grazed. And that gives you the degree to which you have concentrated your herd into a small area. The stocking rate is the mass of the herd divided by the area of the GMU. So this is a density in terms of mass per unit area. The traditional term that people use is in terms of whole animals, which they call stocking units. And this is a different approach, mass per unit area. And then this is the item that the traditional science has sought to fix as a constant for a given area, ecologically speaking, a given region. Okay, so what I'm trying to do is something which is in some sense complementary. Is this where I want to be? Yeah. To what Jacek was talking about. So I'm wanting to distinguish between particular and general models, and I'm trying to ask what could be a useful thing that a general model can do. So if you have a particular model, you have a model and you have actual parameter values in that model, and this model will make you a particular prediction as a function of time, which you would then have actual numbers that you can compare with what you observe. This is a completely different thing. Instead of having a parameter that you try to estimate, you just have a function. This function is actually an interesting quantity, of course, in this case, because it is the per capita rate of change in the population, and that is something meaningful that you can try and talk about. You can try and talk about it mechanistically or in terms of observations and so on. So what I'm wanting to ask is the following. If you have a general model and a given pattern, for what kind of functions in your general model do you actually observe the pattern? So you could ask, for instance, if I'm interested in population cycles, what kind of function will actually give me population cycles in this particular general model? And of course the answer is that there aren't any. You cannot have population cycle in a model like that. So this then is it's an interesting thing to know about this type of model, which is not necessarily without use. It can be very useful to use a model like this in a particular context, but it is not something that can give you any insight in population cycles. The moment you want to talk about population cycles, you are not talking about a model like that. What I want to ask is the following question. If you have a general model for the interaction between the vegetation cover, the vegetation density, and the animal density, under what circumstances can rotational stocking improve cover? So I just want to take a step back. The reason I ask this is that Alan Savory, in a very prominently publicized talk on TED, claimed that holistic management will reverse desertification all over the planet and will also solve the problem of carbon dioxide pollution, because it will draw all the carbon out of the atmosphere and put it into the soil, and we don't have to worry about climate change due to carbon dioxide if only we follow the advice of the Holistic Management Institute. I want to ask, is that actually ever possible? I don't want to ask it in a completely general context. I want to ask it in a more particular context. So the only aspect of what Alan Savory is claiming that I want to talk about is, can you increase the level of cover by the vegetation purely by adopting rotational stocking? So the holistic management people will say, oh, but this is not adaptive stocking, this is merely rotational stocking. But I think that there's a lot of similarities, and under certain circumstances, those two management styles resemble each other a lot. And so I think there's insight to be had to just looking at rotational stocking, which is possible to model in a relatively simple way, which you certainly can't do with adaptive management. Okay, so here's the model that I'm looking at. So I'm going to talk about individual equations there in a minute. What I just want to note here is that I have the level of cover, that's the phi sub v. I have the actual vegetation density and the animal density. And what you should notice is that there are two models. There's a model for the vegetation cover phi, which is almost uncoupled from the model for the densities of the animals and the plants. They're only covered by these two functions, L and R. So in the terms that I've been using in terms of talking about a general model, this is in a sense a general model for the cover under the influence of animal-plant dynamics. This is not, of course, a general model.
Can I ask you one thing?
Yeah?
What do you mean exactly by cover respectral density?
So cover, okay, let me talk about it now, and I'll talk about it later as well. Cover is just a fraction. It's just the surface fraction on which you find plants. So the cover plus the bare add up to 1. I interpret this as in terms of a mean field. So I don't actually talk about real bare ground, real covered ground. It's just the mean field.
What is the density instead?
The density, the plant density is then the grams per meter squared of plants where there is cover. So that is not 0 where there is cover, and it is 0 when there is no cover. Okay, so that I'll give you another chance to think about that in a minute. This is the population dynamics model. So it's got the carrying capacity there. It's got basically Holling type 2 interaction between the plants and the animals. And it's just got a constant mortality for the animals. This is a so-called metaphysiological model. And so these are densities, mass per unit area. They're not numbers of individuals. The V is the vegetation density in vegetated patches. So that's why it's got a K there that doesn't depend on the actual cover. But here, the phi sub V is the actual amount of food in grams per unit area that the animal can see. So this is the density, the V is the density of vegetation in vegetated patches, and then you multiply it by a fraction smaller than 1 because not everything is vegetated. So this is actually the total density of available food. Okay. The plants, however, see the local density in the vegetated patch, so they interact only in terms of the carrying capacity, which is the maximum density the vegetation can achieve at a point. The other component here is the seasonality, which is either 1 or 0 or 2, so that it averages out over 1 over a whole year. So T is just a whole year, and I'm just trying to find a way of writing this. It's constant 0 or 2 half the year. The first half of the year is dry, and the second half of the year is wet. So it's only when you have rain that the plants actually grow, otherwise they just get eaten. So this doesn't, for instance, model the change in the quality of the vegetation. the plants that the animals eat in general in these savannas during the winter, during the dry season, is of very low quality. They barely get any food from it. Many animals just don't eat. They just go through the whole winter without eating or hardly ever eating.
So what does the C stands for?
Sorry?
The C.
This T.
C.
This.
The numerator of the C.
Where? This.
CI5.
This.
Yeah.
That's the conversion. So this is the this is plant biomass, and this is the conversion factor. C is the conversion factor for converting plant biomass into animal biomass. This is typically measured in terms of the dry plant weight, and this is typically measured in terms of the wet animal weight. And so the conversion factor is actually relatively high because it's converting, although in terms of in dry mass terms, the conversion is probably order of 10% or less, but this is, oh dear, this is about 0.7 or so most of the time. So I'm not going to present the parameters that I used in computations for this, but I can give you the parameters if you're interested in. Okay, so this is the cover submodel, and this is the loss rate. So there's a loss rate of covered vegetation to bare as a result of and it depends on H, and this is the rest of it. So this is what is bare, and this is what is covered, and the bare ground recovers at a rate R, and it lost. The cover is lost at the rate L. You can write like that. So you see, this is actually a very simple linear for those of you who want to think about ordinary differential equations. This is just a simple ordinary differential equation. And if H and R, if L and H are independent of phi, then this is just a linear equation. So phi sub v is the fraction covered by plants. It's between 0 and 1. It is to be interpreted as the mean field value. So I'm not interested in the actual structure of bare and vegetated ground. And this is then a rate of change. And if the phi dot is 0.5 over t, then half the sites are becoming covered per year. So that's an instantaneous rate. I'm not saying this is what happens over a whole year. This is just the rate per unit time. This is actually, therefore, a relatively high rate of turnover in the cover. And I'm going to compare high rates and low rates. So this 0.5, I reckon it's a high rate, half of the total area changes. This obviously has a fixed point, which is just R divided by L plus R. And if you regard R as just a multiple of L, then you see that the fixed point is at alpha over 1 plus alpha. And so if alpha is much bigger than 1, then you get a very high level of cover, which means that to get a high level of cover, the rate of recovery from bare to vegetated must be much higher than the rate of loss from vegetated to bare. So that's really what I wanted to get to, was this idea that to get a high level of cover, you've got to make R big relative to L. And so that is what I want to investigate. Under what circumstances can you actually get R to be big with respect to L? So I said I'm interested in general models, but now I'm going to go to a model which is a bit more specific. I'm going to explore what happens with L and R if I assume that L is constant and R is just this simple expression, 2 parameters, R2 times H to the theta. I can actually make an argument for why theta should be 2, but I'm not going to. It's perhaps a weakness in the model that there's absolutely no seasonality. It doesn't matter whether it rains or not. If your level of phi is less than the fixed point, it will grow to the fixed point. If it's more than the fixed point, it'll decline to the fixed point, irrespective of whether there's rain or not. Okay. Now, rotational stocking. I say there's a system with k paddocks that all actually have equal size, and they're all visited for exactly the same number of time, and so the paddock is occupied for a time, capital T over k, and it's rested for the rest of the time. Because the stocking rate is h tilde, when it's occupied, you have an actual density in the paddock of k times h tilde. So this density h here under rotational stocking becomes k times h tilde. Right. So the reduced model, when h is independent of phi, is actually a simple model. All we need is to say that the h level is either this or that. It's kept constant. Of course, you can make h dependent on time in any kind of way you want, but if you do rotational model, this is an interesting one to look at, and it's an easy one, a relatively easy one to solve. I don't want to exhibit all the symbols, but it's a linear equation, the coefficients are integrable and periodic, and so the solution is unique and periodic, and it goes like this. During the occupied period, it grows at this rate, which has this component. So this rate is larger than that rate. During the rest period, it declines at this rate, and during the other, so it goes up from a low level. Then during occupation, it goes up, and then during rest, it goes down, and it forms an attracting limit cycle, which looks something like this. So there's the low level. It goes up. This is k equals 10, so it's just for 1/10 of the year, and then for the other period, it declines. And you can see that the values are relatively low, so the R0 is quite low. And because the R2 is small, it's R0 divided by 4,000, the fluctuation is not very big. Here, the dynamics are relatively slow, 0.05 over t. So I just want to say what I'm reporting there is the average. I'm just taking that average and I'm reporting it here. So this is the I'm wanting to get the average. So the average would be somewhere between the maximum and the minimum. And you can see that when k is 1, this looks almost completely constant. You can't really see that there's any change. Here the dynamics are slightly different. It's still slow, but now the coefficient of the animal presence, the kh tilde to the theta, this R2 multiplying that coefficient is much bigger. It's 100 times bigger than here. So you divide by 40, divide by 4,000. And so here the fluctuation is much higher because the animal effect is much stronger. And if we have a weak animal effect, but a very, very fast dynamic, then the effect is fast up and fast down. And if we now say that not only is the effect fast, but actually the animal effect is strong, then we can have a dynamic which if you look at k equals 10, it goes up virtually to fully covered in the less than 2 months, just over a month that the animals spend in that paddock, and then it declines. But the average of the k equals 10 and the k equals 5 are not going to be equal. In fact, the k equals 10 average is actually slightly lower than the k equals 10. Here the k equals 10 average is bigger. So the take-home message is that rotation in this context improves the average, and in this context it doesn't. So rotation going up to k, and you can imagine that if you go up to k equals 50, it will even improve it even more, and the average gets better and better. But actually here it looks like it doesn't. So this is the framework, this is the experiment, in a sense, in modeling that I've set up and that I now want to explore. So, as I said, I'm trying to work towards something in terms of general modeling, and I'm trying to see if there's some kind of experiments that I can perform on this context which will tell me something that I might try to generalize. So the experiments are as follows. I'm not going to bother with the population dynamics. Keep that constant. There are 4 parameters that I can fiddle with in the cover dynamics, and 2 in terms of management policy. So this is what you can actually manipulate if you have a system that you're dealing with. These are given by the environment. This is under your control. And I want to explore the average cover in the periodic solution as a function of k. As we've seen, theta is influential. I'm going to use these 4 different values for theta. I'm going to have low and high L0, and that sets fast and slow dynamics because the recovery will scale with L0. Okay, so the parameter values that I'm actually using are the following. That is 0.05, that's actually over t, I'm sorry. And then you have a low level of R0. So if R0 is a quarter of L, then this is a level of cover given by these 2 parameters of only 20%. In this case, it's a level of cover of 80%. So the background level of cover, independent of the animals, is 20% here and 80% there. This is the animal effect. Here the animal effect is small. Here the animal effect is 100 times larger. And this is also an animal effect. Here you have a very large number of animals as your target stocking rate, and here you have a relatively small one. Now, there's a lot of combinations. My plots, I take all 4 values of theta and I plot the average cover versus k. So each plot has 4 curves on it. I'm not going to show all 16. I just want to show you 4 that are related to each other. Okay, so here I'm looking at the situation in which h is equal to k times h tilde in the grazed paddock for the whole time, artificially kept that way somehow. And what we see is that if the stocking rate is 50, and this is the low slow dynamics, and this is a relatively high level. I'm not sure of that. I think this is actually the low level of R0. And then this is a relatively high level of R2. I don't know. I can't now remember. If we compare it with this one, what we've changed is that the dynamics are fast. So the only change here is that the dynamics are fast, but we see that those high levels at the slow dynamics decline. And in fact, even this one shows a bit of decline. Only when theta is equal to 1.1 do we see an improvement due to rotation. If we compare, still with fast dynamics, but now we massively increase the stocking rate. I actually can't see my own thing. I'm going to stand here. Now we massively increase the stocking rate, and now rotation is absolutely bad. It's no good to be seen from rotation. Instead of increasing the animal effect by a huge increase in the stocking rate, we can change the R2. And yeah, here I'm dividing by that number. That's why these numbers are small. So this is, in fact, this is a low. You can see that that here the background level is actually very low, 20% or so. And we get this sort of effect. So here there's definitely clearly to be seen that doing the rotation, increasing your number of paddocks, really improves the cover. You can improve your cover from below 30% to over 60%. Just the only manipulation you're doing is you're increasing the concentration factor of the herd as you move it around. So most of the farm is absolutely empty, no grazing happening. There's this small herd which is moving around fairly rapidly. So the other thing that I want to notice is that when your theta is equal to 0, the impact of the rotation is virtually 0. It virtually makes no difference what you do at low values of theta. And that is what I'm wondering one could try and explore, of whether this is possibly general for all of the models of this form, so that you can get revegetation purely by using large K, but it never happens unless theta is quite a bit bigger than 1, and even then it's not guaranteed, which I think the holistic management people will feel that I say it supports them, and they will feel it doesn't. And the blanket claims which have dominated the debate, it's not supported at all. I haven't spoken about the yield at all. I'll talk about it a little bit in a while. But in order to achieve this constant H, you would have to remove all of the gain in mass that's happening as it's happening instantaneously all the time, and you have to remove that. This is clearly impossible, and so that's why we need the full model. Okay, so now let's see what the full model says. There are chaotic solutions. I have explored them only to a certain extent, and I'm not quite sure about the nature of the chaos or how often it happens or whether it's at all important. Again, for the parameter choices that I explored above, there's an attractive limit cycle, as far as I know. Therefore, I can again look at the average phi. But, of course, I cannot achieve a constant stocking rate. So instead, and I don't want to model this pattern where you add and remove whole animals at odd times, because that becomes very difficult to interpret in any general way. So the intermediate between these two extremes is to only occasionally adjust the density, and my choice is to do it at the time that the animals move from the camp. So at every movement into a new paddock, you enforce your target density. So that's not necessarily easy. If you have a research unit, you can have a big farm and all your extra mass can move onto it, and all your if you have to supplement, you can bring it off the rest of the farm. So you can more or less achieve this in an experimental setting, but probably in a practical setting you can't. Then you harvest is the difference. So at the end of a grazing period, you've got a density H in that paddock. And this is what you want the density H to be. So if you've gained mass, you can take some of it off. And if you've lost mass, this will be negative and you have to put in. So this is an illustration of that. In the case of two paddocks here, so the animals are the red curve. You see they start there, and the mass increases for a while and then it drops because the first half of the year is dry, and so the vegetation that's being eaten is rapidly going down. This is the density, not the cover. The cover actually changes very, very little because the animal density doesn't change such a lot. And then you supplement. This is, you have to add this to get it in, so this is a cost. But then the animals can eat, and even though they can eat, the vegetation density still goes up, animal mass goes up, and this entire difference between this level and that level is available as a harvest. So you get harvest. If you do 4, then the animal, again, at the end of the dry season, these two are essentially identical. So you have a loss there, and then you have a gain there and there. And it may be that what you get in total, the average over 4 of these events, is slightly better than you get in the case of k equals 2. Right. So now let's look again at the average cover. And this is the initial situation. And you see that basically everything increases with k except when theta is equal to 1. Here we have a bit of a separation, which wasn't, there's also a separation. This doesn't increase with k. This increases and then decreases. This increases and that remains constant. That's the one we just saw. Here we have with the 2 large values of theta, there's a decline with k, and with a smaller value, there's an increase, and again, there's a decrease there. And on the other hand, if we have a low stocking rate, fast dynamics, a large factor for R0, and a very small R2, I'm sorry about this confusion, you do see that the cover can recover from 30% up to 80%. So that's a much bigger change than we had for the previous model. Okay, I want to also just put them next to each other. So this is the same set of parameters. This is the constant h, and this is the one which is dynamic, where you have to change the actual h level at the end of every camp. And you can see they're very similar, but they're not quite the same. Again, they're rather similar, although in this case, this one just drops and that one goes up and then drops. So there are small differences. Here, the behavior is different. So this is the one with a large animal density, fast dynamics, small r, big R, but small animal impact. And here, because of the animal dynamics, you actually get something different. You can get a situation where the cover improves with k, which you don't get on this side. And again, these two are then very similar. You get the improvement. You get the improvement with k, small fast dynamics, low animal density, and very weak impact by animals. Okay, so Jacek spoke about models being shown to be wrong if there's a counterexample. I'm talking about models where you have, instead of a counterexample, I'm offering a kind of existence proof, which is that rotation using large factors can facilitate revegetation, and it works in much the same way in the full model as in the reduced model. It may be that theta greater than 0 is necessary, which means that doubling h more than doubles, oh my word, that's terrible. It's r sub 2 times h to the tilde. Okay, my typing is, and my proofreading for that matter is out. I want to point out that in one dimension, if you multiply your rate by k, but you reduce your time by a factor of 1 over k, that is actually doesn't change the outcome at all. In higher dimensions, you would have the same result in higher dimension if the matrix had the same eigenvectors over the 2 time periods, but it doesn't, and so this doesn't generalize to higher dimensions. So this is a suggestive idea, it doesn't generalize. I've looked at this formally, and I don't get that the derivative of phi bar with respect to k is 0 at theta equals 1, but it is very, very small. So there seems to be something here, but I haven't actually found a way of pinning it down. But I think there's a general result there. One should also say that large parts of parameter space do not, in fact, have the revegetation. You have average cover declining. I just want to make a few comments about the harvesting. So this is just a formal description of what I spoke about. So it's the difference between the left and the right-hand side, except that you subtract the right-hand side from the left-hand side to get the harvest. And you have to divide this by k because we don't want it relative to the paddock, we want it relative to the whole GMU. So we've got to take away the concentration factor, and effectively that means that when we take it over the whole year, we just take the average of all the harvests. So these first 2 harvests were negative, the next 2 are positive, and so we get a net harvest density which is positive. So this is older results, and I'm sorry that the graphics aren't so great. What I want is, and also that these are different parameter values. But here you have very, very slow dynamics. You have a low H naught. You have a relatively small R naught. So here you have a half over 3 halves. So this is 1/3, the background level of 1/3, and a relatively large R2. You see that because of these factors, you get quite good harvest densities, relatively large, but they decline with K. So although you might have increasing cover with this particular, this is a good system for getting good cover, your harvests just go down with K. So you have to really believe that you really want a well-vegetated farm because you're not actually going to get very good harvests. Here, the R naught is very low, the 1/200. Basically, the background cover level is 0. And the R2 is very small. And so that's why these harvest densities, although the target stocking rate is only 60, they're negative. You have to spend an enormous amount of bringing in of outside cattle to keep stocking at minus 60. Basically, all of your cattle just die off unless you have a large theta. Then, as your number of paddocks increase, you start, but you see that the increase is slowing. You're just about at 0 when this is 13. And if you continue on beyond, it's doesn't get a lot better. But here is a situation where you do get an increase, and it looks like it's going to be increasing. So again, these are negative unless theta is large. So here you have a strong response in terms of the factor of the power theta, and that's enough to pull this system from one which would be loss. It would be a loss without rotation, and it's a bigger loss with rotation unless your theta is large. Okay, so that's it. Right.
Questions?
Andrea.
Why should the recovery rate increase with the higher power of animal density?
So my argument for theta equals 2 is the following. There's been a lot of debate in the experimental literature of the impact of animals on the vegetation. When the animals spend time on the vegetation, they fertilize the area and they disturb the soil, which might encourage germination. They also, in certain contexts, you get a lot of self-shading with dead plant material, and they will trample that down. So they enable buds and things that are at the base of the plant to come out. So there are lots of possible facilitations. The reason why you might say that is proportional to the density squared is that all of those have to do with the animal's foot action. And you might suggest that the animals respond to animals near them, to the social interactions with each other. They pay attention to the animals near them, and so they step on the grass more in order to just accommodate. And that, of course, is proportional to the local density squared. So that's one possible reason why they should respond non-linearly.
There is experimental evidence for that?
Of this?
Yes. Or it is just like
No, this is just my imagination. I've spoken to one or two people in experimental context, and I've said to them, this will only work if the effect is nonlinear in the density, and then they nod. They say, yes, yes. They think that's absolutely right.
Yeah. Just one silly comment. This takes me back 45 years, because Savanna actually is a model, and he was peddling this thing like crazy, and he received just as much flack back in those days as he did. And they did actually do the experiment.
I've got the data, yeah.
Charter Estates in the 1970s. I heard him on the radio, and basically what he was doing exactly what you were doing. He's saying, well, maybe it worked, and maybe it doesn't work, and he couldn't actually do it. The other silly comment is he started off life as a tsetse control officer.
He killed a lot of elephants, I believe.
Probably that too, yeah.
Yeah. Yeah, yeah, he was involved. He gave the advice that elephants should be removed. Apparently.
more question.
Yeah. Yeah?
So how then do you become confident that the numerical experiments that you have are correct without any experiments, without any data?
So obviously, I'm not going to claim that they represent anything in the real world unless I have data. But actually, it wouldn't be difficult to reproduce data from the real world because I've got a lot of parameters that I can play with. I don't think that making these curves fit observed curves would mean anything at all. So I'm much more interested in the possibility that there's a general rule. That if you want to claim, if you're an adherent of holistic management or any other intervention that you claim you can use the animals as ecological engineering, I want to be able to say that I've got a really good case that you have to have a really special environment where the response of the plants to the animals have a certain nonlinear property. And if you don't have that, you can't even begin to make that claim. Because I'm saying that this is the general structure. Or if this kind of model describes a general structure, then for this effect that you want to claim, you would have to show that your environment and the species and so on have this kind of interaction. That's what I'm really looking for.
But like I could also maybe come up with a different sort of model I claim that possibly it's.
Are you saying you'd come up with a model that doesn't fit this structure?
Yes, yes. And I'll claim maybe it's the best model then.
Well, of course you could. I mean, you could come up with a model that was based on the Bible, or that was purely climate-driven or something. There are more models than data. The world. You can imagine more worlds than there really are. So my claim would be that if you want to understand this in terms of a dynamics which fits into this context, then I want to say there are certain kinds of properties that you have to respect if you want to get a certain outcome. That's kind of the strategy that I'm looking for. Mm-hmm. No? Too many equations.
Okay, thank you very much.
Thank you.